This is Unit 1, Our Place in the Universe, Day 3. Our learning targets for today are 1C, our stellar life cycle, or our star life cycle. We'll be able to contrast the lifespan and energy output of a blue giant star to that of the Sun, and relate this to the potential existence of life on planets in its orbit, and analyze the various fusion products of a blue giant star over its lifetime and relate this to the presence and abundance of elements that make up our solar system. So what is a star? A star is a large, dense concentration of hydrogen gas that exists and collapses under the influence of gravity. It changes as it ages because its composition changes. In other words, it changes what it's made of. Fusion reactions in the core convert hydrogen to helium. This is what gives off all of the energy. As you fuse two hydrogen atoms together, a large amount of energy is given off that we see as light, and this fuses them together and makes helium. When a star actually runs out of hydrogen, it dies. So when we look up in the night sky, we usually see constellations. All these are groups of stars that form a pattern, and they tend to move across the night sky. They appear to move because Earth is spinning, or it's due to Earth's rotation. They're going to also change throughout the year as we go around the sun, or as Earth orbits the sun. Stars are going to follow a definite development and destruction pattern that is referred to as its life cycle. It starts out and it's born, and then it eventually is going to die. All of our stars are born in a solar nebula. That literally means sun cloud. So a solar nebula is a cloud of gas and dust that forms a star. This goes back to our solar nebula theory, the formation of our solar system. When we have our solar nebula, the material in the very center of that nebula is what is going to become the star. We call that the protostar. As the protostar starts to shrink, our temperature and pressure are going to increase. Now it's shrinking because gravity is pulling all of that matter together. When the temperature and pressure are high enough, it is going to ignite or start fusing hydrogen into helium. At that point, our star is born. Now, mass is going to control the evolution, lifetime, and the ultimate fate of all of our stars. And we can see on this diagram, this little protostar down here has a very low mass. It's only going to become what we call a brown dwarf. This one has a little bit more mass. It's going to become a red dwarf. Even more mass, it becomes a sun like ours. Even more mass, it becomes what we call a blue supergiant, and on and on. Now you notice these take on certain colors. We have brown, red, yellow, and blue. This is just like flames when you light a fire. At first you're going to see some reddish flames. Those are your cooler flames, and then the flames will become more yellow. Those are burning hotter. And eventually you might be able to see a little bit of a blue flame in the center. That is a very, very hot flame. The color of our stars can also tell us the temperature that they are at. So we have what's called our main sequence stars. This is the most stable phase of our star's life. This is considered the middle age. So first it becomes a protostar, then it becomes a main sequence star, and depending on its mass is going to tell us how it's going to die after that. So a star is going to spend most of its time in the main sequence. Our sun right now is a main sequence star. The life cycle for an average mass star. Our sun is considered an average mass star. It begins its life as a protostar in the center of a solar nebula. Once it begins fusing hydrogen into helium, it becomes a main sequence star, where it's going to spend most of its life. As it starts running out of hydrogen and can no longer fuse a lot of helium atoms, it's going to start to swell into a red giant star. After some time as a red giant, it's going to explode in a nova, which is a sudden large increase in brightness, and create a planetary nebula. Now, a planetary nebula is a cloud of planets. So the sun will disappear and collapse into a white dwarf or a black star and leaves the planets rotating around it. Now, our dwarf stars, we have two types. Thankfully, they're named very easily. We have our white dwarf. They're blazing hot. They look white. It's going to be a very small star, and it takes them millions of years to cool off. Eventually, it will become a black dwarf, called black because it's no longer giving off light. It's a cold star, and it's our dead white dwarf. Now, when we look at the life cycle for a massive star, one that starts off with a huge amount of mass, it again begins as a protostar in a solar nebula. Then, because it has so much mass, it's going to burn hotter, so we call it a blue giant. Again, when it starts to run out of hydrogen, fuse into helium, it's going to swell into a red supergiant, much bigger than our red giant. Eventually, it's going to explode in what we call a supernova, which is a huge, massive explosion. After that explosion, it's going to collapse into an extremely dense ball called a neutron star. Eventually, it becomes a black hole. Now, sometimes it can skip being a neutron star and immediately become a black hole. This all depends on the mass of the star. So our star is the sun. It's the star at the center of our solar system. All of our planets and all other objects are going to revolve around the sun. It is 1 astronomical unit, that's abbreviated AU, from Earth. So if we take the distance, which is 150 million kilometers from us to the sun, it is considered 1 astronomical unit. So the sun is enormous compared to the Earth. It's over 1 million Earths would fit inside. I love this picture because here's our little teeny tiny Earth right there. And it's fitting through, this is called a prominence, coming off of the sun's surface. So you can see the size difference there. Our sun is going to be made of mostly hydrogen gas. The energy that it gives off comes from nuclear fusion in the core. So it is taking our hydrogen and it fuses them together and it becomes helium. This process gives off lots of energy. That's what we see as our light. So when we look at the inner layers of the sun, just like everything else, it has a core at the very center. This is where our nuclear fusion occurs and creates the sun's energy. It's the densest layer of the sun. Its density is over 10 times that of lead. Next layer out is our radiative zone. This is a region of tightly packed gas where energy moves as electromagnetic radiation. It's moving as radiation, so we call it the radiative zone. Our next layer out, our convective zone. This is where our hot gases rise from the bottom of the convection zone and cool as they reach the surface, so they start to sink. Cooler gases sink, forming loops of gas that move energy towards the sun's surface. So we have our hot stuff going up, and it cools a little bit and it comes back down, gets heated by our radiative zone and heats back up and rises back up, and it goes back down. This process is called convection. That's why it's called our convective zone or our convection zone. Now looking at the outer layers of the sun, what we would call its atmosphere. First we have our photosphere. This is the visible surface of the sun. Photo means light. So when you take a photograph, you are trapping light on paper. Next we have our chromosphere. Now chromo means color. So this is a thin colored gaseous layer present above our photosphere. This is the part that we see as the color. Depending on the temperature of this is going to tell us what color. If it's a little bit cooler, it will be red. If it's a little bit hotter, it will be yellow. And very hot, it would be blue. Finally, we have our corona. This is our outer atmosphere that is only visible during a solar eclipse. It gives off a stream of charged particles that we call our solar wind. And corona literally means wreath or crown. And when you see it after a solar eclipse, it looks like a jagged crown going around the sun. So surface features that we have on the sun, we have sunspots. These are them there. They are literally dark areas on the sun that are cooler than the surrounding area. So underneath this is probably where we have our cooler stuff sinking in our convective zone. The number of sunspots varies over an 11-year cycle. So sometimes we'll have a lot more, and then other times we'll have a lot less. We have our prominences. These are loops of gas that link sunspot regions and are the cause of our auroras. If you've ever been towards the North Pole or towards the South Pole, you've seen the auroras in the night sky. That is the solar winds coming up of prominences that interact with our electromagnetic field and cause lights in the night sky. We have our solar flares. These are explosions that occur when sunspots suddenly connect. So our flares, it's literally a jet of sun material that is coming out.